Classical AI scaling laws remain highly predictive across vastly different model architectures, precisions, and training regimes. We express this predictability through a standard power law equation. Loss is proportional to compute, raised to the power of a negative constant. The central variable here is C for compute. The professional misconception is that this variable represents a physical tally of resources. We assume C stands for the hardware used, the megawatt hours consumed, and the calendar days spent training. It does not. C in the classical law is an abstraction called logical compute. It measures mathematically pure model-side work. It is completely divorced from the physical hardware used to execute it. Treating logical work as physical hardware limits our analysis. It blinds us to the hidden efficiency metrics that actually dictate whether an AI project scales successfully or runs out of capital. Logical compute assumes a dense, uniform precision reference model. It operates without any clever software tricks, sparse routing, or quantized parameters. It is pure math. Physical resource burden is the absolute real-world cost incurred to run that math. It is the raw electricity drawn from the grid multiplied by elapsed calendar time. Connecting the abstract mathematical work to the real-world cost requires a governing variable, logical efficiency. This term measures how effectively a specific stack of hardware and software translates raw physical joules into abstract logical work. A singular mathematical scaling target can demand vastly different amounts of power and time. The physical cost depends entirely on the strength of this hidden efficiency layer. Machine learning engineers already track system efficiency. They typically use model flops utilization, or MFU. MFU divides realized throughput by the hardware vendor's stated peak performance. The flaw lies in the denominator. Vendor peak relies on variable conventions and fluctuates across marketing materials. Logical efficiency replaces this unstable number with physical ground truths, elapsed time, and power draw. MFU evaluates software against hypothetical hardware potential. Logical efficiency measures abstract compute against the absolute limits of thermodynamics and the calendar. Using an absolute resource baseline allows us to track the true burden of scaling across entirely different computing systems. MFU confirms your code runs well on a specific GPU. Logical efficiency determines if your local power grid can actually sustain the training run. Diminishing returns dictate that each subsequent reduction in loss requires a disproportionately larger amount of compute. To push a target loss near the irreducible floor, the required volume of logical compute explodes outward. We can plug that massive logical compute requirement straight into the numerator of our physical burden equation. As we approach the limit of the loss curve, the sheer physical demand for kilowatts and hours begins to scale exponentially. Consider what happens if the efficiency term in the denominator remains static during this push. With a static denominator, an exploding numerator translates directly into impossible electricity demands and training times spanning decades. This is the operational reality of the scaling exponent. Geometric flattening on a chart and escalating operational burden in a data center are identical conditions described in different domains. Diminishing returns represent an escalating physical crisis. They will forcefully halt progress unless the underlying efficiency architecture changes. To evaluate real-world AI progress, we must index the static scaling equation to elapsed calendar time. We assume the physical resource budget contributed by the industry grows linearly, or stays roughly constant year over year. We then introduce beta, the annual efficiency doubling rate of the entire hardware and software stack. Beta transforms static efficiency into a dynamic compounding exponential function. This compounding rate mathematically dictates how rapidly logical compute accumulates as years pass. We substitute this dynamic compute accumulation back into the excess loss form of the classical scaling law. This yields relative excess loss, the remaining distance to the irreducible loss floor, tracked against the calendar. The classical static law sets exactly how much logical compute is required to reduce error. The time-indexed extension dictates how quickly that compute actually becomes available to engineers. The static equation establishes the price of intelligence. The dynamic rate of efficiency doubling determines if we can pay it. This chart maps relative excess loss on the y-axis against calendar time on the x-axis, holding the scaling exponent fixed. Look at the dashed line. This represents a beta of 0, no efficiency doubling. where physical compute only scales linearly with investment. The excess loss barely drops. Progress effectively stalls. The solid blue line represents a historical, more like baseline of 0.5, meaning efficiency doubles every 2 years. Because efficiency compounds, it accelerates the accumulation of logical compute, forcing the error rate down continuously. Observe the 20-year divergence. A slower doubling rate, shown in red, fails to keep up with an aggressive doubling rate, shown by the steep dive of the black line. Every trajectory here operates under the exact same classical scaling law. The variations arise entirely from how efficiently the physical stack supports the math. The data proves that building bigger data centers is mathematically insufficient. The AI industry relies on a relentless, compounding reduction of physical inefficiency. This doubling rate connects abstract mathematics directly to the daily design choices of systems architects. Engineers deploy lower precision math, like FP8. They optimize communication kernels, and they construct complex sparse routing protocols. We see this in the mixture of experts architecture, utilized in highly optimized models like DeepSeek v3. These system-level innovations do not bypass or rewrite classical scaling laws. They exist as mandatory responses to the pressure of diminishing returns, engineered explicitly to drive up logical efficiency. The classical scaling law dictates what logical compute buys. The efficiency stack dictates what that compute costs. Driving down that physical cost is the only mechanism that keeps the model scaling.